Section 9.7, Polynomial and Rational Inequalities. So here in our last section now we're going to look at how to solve a quadratic inequality first. And we do that by graphing the first method. I'll show you how to do this. So a quadratic inequality is going to be a quadratic expression of the form ax squared plus bx plus c. It has to have that x squared term in order to be a quadratic. But now instead of an equals in an equation, we have an inequality, one of the four inequality symbols, a less than, a greater than, less than or equal to, greater than or equal to. So this is going to be a little bit different than graphing what we looked at in 11.5 when we were graphing the inequalities that involved a y is greater than some sort of quadratic with x squared. This is just taking the quadratic and saying whether it's less than or greater than 0. So if you recall, if we set a quadratic equal to 0 and find the two x values that make the quadratic equal 0, that actually provides us with the x-intercepts of the parabola if we were to graph it. So it provides the x-intercepts of the parabola of the equation y equals ax squared plus bx plus c. Okay. So solving a quadratic when we set it equal to 0, finding those two x values actually tells us the x-intercepts of the graph, where it would cross the x-axis. Okay. So if saying where does it equal 0 finds you the x-intercept, if we have an inequality of a quadratic that is saying less than 0, that is asking us where is it below the x-intercepts. In other words, where is it below the x-axis. And in a quadratic that has is set to greater than 0, that's asking where is it above the x-intercepts, where is it above the x-axis. Okay. So where is the graph below the x-axis? Slide this over. And then saying greater than 0 is asking pretty much where is the graph above the x-axis. Okay. And when I say where, we're asking for what x values. Okay, for what domain is the graph above or below that x-axis. So if we were given an inequality like x squared plus x minus 12 is less than 0 or is greater than 0, what we first want to do is look at it as if it was set equal to 0 and solve in order to find your two x-intercepts. Okay, I already have them graphed over here, but we can review that process real quick. First thing we want to do is find the x-intercepts. Okay, it's already set equal to 0, so we would want to factor because it's an x squared equation. So we'd be looking for two numbers that multiply to give us negative 12, that add to give us a 1 there. So that would factor into x plus 4 and x minus 3 equals 0. Okay, 4 times negative 3 gives you negative 12. 4 plus negative 3 gives you 1. So that then tells us our x-intercepts are going to be the order pair. What makes this parenthesis 0 would be a negative 4. So negative 4, 0 is one of our x-intercepts right there. And then a positive 3 would make that parenthesis equal 0. So 3, 0 is our other x-intercept. Okay. So this right here is the graph of the equation y equals x squared plus x minus 12. Okay. So even though the actual problem didn't have say anything about a graph, didn't say y equals, we can just kind of graph it by, using the x-intercepts, and we know it's going to open upward because it's a positive x squared. Positive x squared. So it doesn't really matter in these problems if we know where the vertex is. All we need to know is that it opens upward and that now we know the two x-intercepts, -4, 0, and 3, 0. So to answer part B, because the answer to part A would be telling the two x-intercepts, -4 and 3. The answer to part B is going to be asking where is it less than 0, so where's the graph below the x-axis. And it's below the x-axis for this little bottom loop here, from -4 all the way to 3. We look at the x values. Okay. So where's the graph below the x-axis? So we can look here from this value right here. This is a -4 all the way to here, +3. Okay, so this is where it's less than 0. This is where it's below the x-axis. Slide this up. However, we always want to write this in interval notation. Remember, interval notation is where we either use parentheses or brackets. So to say from -4 to 3, we write that as -4, comma 3. But then because it is strictly a less than symbol and doesn't have the equal to bar underneath it, we would use parentheses. So to say from -4 to +3. So pretty much what we're doing is we're describing all of this area. So even though we're looking at the graph, where's the curve below the x-axis, we're actually giving x values along the x-axis from -4 x value to +3. Okay. That's where it's less than 0. To then answer the question, where is the quadratic greater than 0, we're now asking where is it above the x-axis. Okay. Well, this is going to have two different intervals, two different sections where that's the case. You can see here on the left part of the graph, it's above the x-axis from -4 all the way forever. As you move to the left, that graph is going to be rising upward. So pretty much we're describing all of this from -4 all the way to the left forever, which approaches -infinity. Okay. So again, we have a parenthesis here at -4, and then we'd be going to the left forever. So we want to describe that as an interval. But then also it's above the x-axis after we've passed 3 and moved to the right forever. That graph is going to be above. It's never going to, it's always going to be above the x-axis because it's moving up and up. So here we want to also describe from +3 to the right forever, which approaches +infinity. Okay. So here we'd want a parenthesis at the, not a 4, at 3, and then moving to the right forever to describe that interval. So we have two separate intervals we have to give when we're saying where is the graph greater than 0, where is it above the x-axis. So to say from -infinity all the way up to -4, infinities, remember, always get parentheses, and the -4 is going to get a parenthesis because we are dealing with a greater than symbol, and it doesn't have the equal to bar underneath it. To describe the second interval to the right is all the way from parenthesis 3 to +infinity. Okay, that tells us 3 all the way forever to the right. It's going to be above the x-axis. And then when we have two intervals, if you recall, we put a u in between them to say the union. It could be inside this interval or inside that interval. Okay. And that's how we can solve these inequalities graphically, by looking at the graph of the quadratic. Okay. Let me slide this up and we'll look at a new example. Alright, so here we have the quadratic -x² minus 3x plus 10 equals 0. So first of all, I do have it graphed on the right, although in order to find these two x-intercepts is a little tricky because we have a negative x squared. So what I would do in order to solve this, to find those two x-intercepts, is rearrange the equation to make the x squared become a positive, and then try to factor. Okay. So if we did that, we would be moving the x squared over to the other side, which would make it a positive x squared, a minus 3x over to the other side, which would make it a positive 3x, and then a positive 10 to the other side, which would make it a minus 10. Okay, and since we moved everything to the other side, now there'd be nothing there, so that equals 0. So if we factor this, it'll give us our two x-intercepts. Okay, but because our original quadratic is a negative x squared, it would open downward. Okay, so factoring x squared plus 3x minus 10. We are looking for the two numbers that multiply to give us negative 10, that add to give us 3. Those numbers are going to be 5 and negative 2. So it would factor into x plus 5 and x minus 2. Okay. So that tells us our two x-intercepts are going to be a negative 5 and a positive 2. And that's why we have our two x-intercepts there at negative 5 and positive 2. Okay. So that gives us that part. We know it's going to open downward because the original equation is a negative x squared. And what we have pictured in front of us, I guess now, is the graph of, this is the graph of y equals negative x squared minus 3x plus 10. We have our x-intercepts drawn in, and we know it opens downward. Okay. So let's solve the two inequalities now for part B and part C. So part B, we are asking, essentially, since it is less than or equal to 0, we're asking where is it below the graph or touching, where is it below the x-intercept or touching, because when it has that equal to bar, it means it can be equal to 0. So below, because it's a less than or equal to, this is below or touching the x-axis. So looking at our graph, we have two intervals where it's below the x-axis. This left part of the graph and then this right part of the graph. Okay. So to describe this left part of the graph, we want to say all of this and to the left forever on towards negative infinity. In this case, we have a less than or equal to bar, so this is where you get a bracket. So we'd say here from an x value of negative 5 to the left forever. Okay. That's one segment where the graph is below the x-axis. But then also over here, from an x value of positive 2 to the right forever, it will always be below the x-axis. So for that, we say another bracket again, because again it has the equal to bar in the symbol, inequality symbol. So from 2 to the right forever towards positive infinity. Okay, as you move to the right. So now we need to write the two intervals and put a u in between them, like we did in the last example. So from negative infinity to all the way up to negative 5. Remember, infinities always get parentheses, but now here the negative 5 will get a bracket. Then we have a u, and then from 2 to infinity, bracket on the 2, comma, infinity always gets a parenthesis. Okay. So kind of ignore that negative infinity for a second that I drew in there. So here is what your actual answer will be, writing an interval notation with a u in between the two intervals. Alright, so then in this graph, the less than was the two intervals, The greater than or equal to 0 is going to be where it's above the x-axis. That's only one interval, just this loop here. That loop goes from -5 all the way to +2 as far as your x values go. Okay. -5 here. We're going to have a bracket there all the way to +2 here. Okay. This is where the graph is greater than or equal to 0 because it's above the x-axis. Whereas our other two segments, this is where the graph was less than or equal to 0, less than or equal to 0, because it's below the x-axis. So our interval here, greater than or equal to, is going to be describing where it is above the x-axis or touching. Again, that's what that equal to bar means in the inequality. Where is it touching? Whereas the greater than part says where is it above. So from -5 to +2. Those are the x values for which the graph is above the x-axis. Okay. So that's how we solve these inequalities if we were to look at it graphically. We have another way we can do this, which is called the interval test. And we'll look at that option now on the next page of the notes. Alright, so now we have solving quadratic inequalities using interval test numbers. So here's a similar quadratic inequality. Okay, we have x squared plus 2x is less than or equal to 8. First of all, we don't care to compare it to 8. We like to compare it to 0. Because then saying less than or equal to 8 is saying or less than or equal to 0 is like saying where is it below the x-axis, above the x-axis, like we just looked at. So any problems like this, inequalities where the inequality isn't set equal to 0, we want to find our two important x values, in other words our x-intercepts, by taking this, turn it into an equation and set it equal to 0. And then once we have it set equal to 0, we either factor, just like we did in the two previous problems, we factor to find your x-intercepts, or what we're going to call it now is the cut points. If it's something that you can't factor or is tough to factor, you always could use the quadratic formula. Okay. In order to find your zeros. Alright, so in order to solve this, let's turn it into an equation. Just change that to an equal sign for now, just to find our two zeros. And we want to move the 8 over to the left side, so it's going to become a -8. So if x squared plus 2x minus 8 equals 0. Okay. If it's a +8 here, it becomes a -8 when we move it to the left. That's easy enough to factor, so we don't really need to use a quadratic formula. Two numbers that multiply to give you -8 that add to give you +2. So that's going to be a -2 and a +4. Okay. Those two numbers multiply to give you -8 and add to give you +2. Okay. So from there, we can find out what our two x values are, our two zeros that give us zeros here. It's going to be x equals +2 or x equals -4. Okay. So just like when we were looking at the graphical method, these would technically be our x-intercepts. So when we do it this way, we still want to draw a number line, just a horizontal x number line, and we use -4 and 2 as our cut points. Okay. So I'm going to call these that. call them cut points. And we want to make a line graph of intervals that these cut points now create. So our graph is going to go from negative infinity positive infinity, just like our x-axis would. And we know what our two x-intercepts would be, -4 and a +2. So you'd have a -4 over here, a +2 somewhere over here. That's all we need to draw on the number line, and because we have two cut points, we actually have three different sections, three different intervals it just created, those two cut points created. We know at -4, the value of this quadratic would be 0, and at 2, the value is 0. We know those are the two x values that make the quadratic equal 0. So that means to the left, of -4, in between -4 and 2, and to the right of 2, it either has to be greater than 0 or less than 0. And what we care in our problem is to see where is it less than or equal to 0. So what we do is we pick a value from each interval to test in the inequality, our inequality from back up here. So let's write that down. Pick a value from each interval to test it in the inequality. In the inequality, remember we moved the 8 over. The inequality is actually x squared plus 2x minus 8 is less than or equal to 0. Okay. We set it equal to 0 in order to find the two x values. But now to actually answer the question, it's in the less than or equal to inequality. So we can call these three intervals that we just created on our number line. We could call this interval A, this interval in between -4 and 2, interval B, and then from 2 to infinity, we'll call that interval C. Okay. So we have to pick a number from each interval, plug that number into our inequality, and see if we get a number that is less than or equal to 0. If it is, then that interval is part of our solution. If we get something that's greater than 0, then that interval is not part of our solution. So our first interval, interval A, we need to pick a number that's somewhere here to the left of -4. So -5, okay, was something that would be in that region. So if we use -5 and we plug that into the inequality, we would have -5 squared plus 2 times -5 minus 8. Okay, just using the inequality right there. Evaluating that, it's going to give us 25 minus 10 minus 8. That actually is going to give us a +7. Okay, is +7 less than or equal to 0? No, it's greater than 0 actually. So that's I guess what happens here is we get a false statement because it's not less than or equal to 0. It's actually greater than 0. So we don't include region A, interval A, as part of our answer. Okay. So what I like to sometimes do is come back here to our number line, and that tells us everything in region A is going to be positive answers. They're all going to be above 0. And we want numbers that are less than or equal to 0. So then we have to check region B. Or interval B. Okay. If you can use 0 ever as your number that you're going to test, then you want to use it. and 0 is in between -4 and 2. So I would say let's use 0. So plugging 0 into the expression here, we have 0 squared plus 2 times 0 minus 8. And the reason why 0 is a nice number because 0 squared is 0, plus 2 times 0 is 0, minus 8 gives us a -8. Makes it easier to evaluate. Now, is -8 a number that is less than or equal to 0? Yeah. Any negative number is going to be less than 0. So that ends up getting us something that we wanted. That's a true statement. Now we get 8, a number that's less than or equal to 0. So we use that as part of our solution. Interval B. Okay. Then we have to check interval C to see if that's part of our solution as well. So we need to pick a number in interval C, which is anything to the right of +2. So we can use 3. Okay. So plug 3 into the inequality. 3 squared plus 2 times 3 minus the 8. And actually, if you do that, that also gives you a +7. And so, once again, it's not something that's less than or equal to 0. It's actually greater than 0. So that's a false statement. We don't want to take that as part of our solution. Okay. So to answer our question, where is x squared plus 2x minus 8, where is it less than or equal to 0? Well, only in one of those regions. We can call it in region B, or interval B. So we just want to write in interval notation what is region B. So going back up to the graph, kind of filling this in, I forgot to before. Interval B gave us a negative number. That means everything from -4 to 2 is going to give us negatives. And then everything in region C was positive. So our actual solution is going to be everything from -4 to 2. That's what interval B is. And because it's less than or equal to, we end up using brackets. Okay. So our answer in interval notation is -4 to 2. Bracket and bracket. So then I think in my math lab assignments, they'll ask you to draw a picture of the graph or choose the correct graph, multiple choice. So the graph is pretty much just what we have up here. Okay. So we have -4 to +2. And everything should be kind of drawn in, shaded in from -4 to 2. Okay. All right. So that's what most of the examples will be like. Although the next example I have looks a little bit different, but is actually easier to solve because it's already in factored form. Okay. I guess to kind of compare it to what we just did, remember we took our inequality, got it set equal to 0, and then factored the left side to find out what were our two zeros, what were our two cut points. Well, looking at our next example, we're already in factored form, right, the parentheses form. So, problem like this, we don't have to worry about getting it factored. It already is set with a 0 on the other side. We can just think of this as x plus 5, x minus 3. What x values is going to make that equal 0? That's how we find our cut points. So this tells us x either is going to have to equal -5 or x is going to equal positive 3. So from that, we want to graph our intervals on a number line like we did above. So from negative infinity to positive infinity on our number line. Okay. We want to mark off negative 5 and positive 3. So this is going to cut our number line into 3 intervals again. Interval A, interval B, and interval C. We know at negative 5 and at 3, our function equals 0. So we want to see, in interval A, B, and C, do we have positive values or do we have negative values? Because our solution is going to be all of the sections, all of the regions that give us something greater than 0. In other words, give us positive answers. So that's what we have to now test. We want to use that interval test again. So we're going to test where x plus 5 times parentheses x minus 3 is greater than 0. Okay. So let's pick a number in each interval, starting with interval A. Interval A is everything from negative 5 to the left. So we could pick a number like negative 6. That would be in that interval. So we want to plug negative 6 into this inequality for x. So in the first parentheses, we'll have negative 6 plus 5. Second parentheses, we'll have negative 6 minus 3. If you multiply that out, that'll give us negative 1 times negative 9, which is going to give us positive 9. Okay. Well, does it give us a true statement based on our inequality? Yeah, it gives us something greater than 0. So that checks. There's a true statement. So we know interval A is part of our solution because we got ourselves a positive answer. Then check interval B. Remember, if 0 is in the interval, use 0, and 0 is in between negative 5 and 3, so let's use 0 for that one. So plugging 0 into the inequality, we're going to have 0 plus 5 and 0 minus 3, which is going to give us 5 times negative 3, which will give us negative 15. Okay. Well, will negative 15 work in our inequality? No, that gives us a number that's less than 0, and we wanted things that were greater than 0. So we don't use that as part of our solution. Lastly, we need to check interval C. So any number to the right of 3 on a number line, so we can use 4. So we have 4 plus 5 in the first parenthesis, then 4 minus 3 in the second parenthesis. And it's going to give us a 9 times a positive 1, which equals 9. 9 is greater than 0, so that checks as well. That's all we need is something greater than 0. So region B gave us negatives, region C gives us positives. So both region A and region C are going to be part of our solution now. So So again, to answer the question, where is x plus 5 times x minus 3? Where is it greater than 0? Well, region A and region C. So we have to write that in interval notation. This is strictly a less than symbol. So we are going to end up having parentheses from negative 5 to the left and from positive 3 to the right. If it had the equal to bar, then we would have had brackets, but it's just strictly a greater than symbol. So our region should be negative infinity to negative 5, parentheses, union positive 3, comma, positive infinity, parentheses as well. Okay. So either of those two sections. And then to answer what the graph would look like, it would look just like that. Okay. Negative infinity, our number line would go from the negative infinity to positive infinity, negative 5, positive 3, and we'd have a parenthesis at the negative 5 and everything to the right shaded in, parenthesis at positive 3 and everything to the right shaded in. Sorry, everything to the left shaded in from negative 5, everything to the right of positive 3. Okay. So there's our solution. Alright. Now using that inequality test, you could either do this method to find the inequality, the answer to an inequality, or you could use the graphical method we did on the first page by graphing the parabola and seeing where is it above or below the x-axis. Now, when we look at, we're going to look at some special cases now, and then actually a rational inequality. Okay, a rational inequality is going to be when we have some of those crazy looking fractions that have variables in the numerator and denominator. When you do rational inequalities, you have to do the interval test that we just did, where you make the cut points, because I'm not really going to get into showing you guys how to graph those. It's a little bit more than we need to worry about at this point. So you might as well get good at doing that interval test that we just worked on, because you'll have to do it for the problem like this. But let's first talk about the special cases when we still have quadratics. Okay, sometimes you'll be given quadratics in this form. Okay, it's a quadratic because it has the power of 2 outside of the parenthesis. So if you were to FOIL out the expression, you would end up with an x squared, which is what a quadratic is. Okay. So center this up. So the special cases. First thing to notice, we have something squared, okay, something in parentheses being squared, and it's saying where is that, well, for what x values is that greater than negative 1. Okay. Well, in this whole section, if you catch this, it'll make these problems a lot easier. If you remember that if you square anything, whether it's a negative or a positive number, squaring it means multiplying it by itself. And anytime you take a number and square it, it's going to equal a positive. Okay. So it doesn't matter what we put in here for x, 2 times that number minus 3, whatever we get, if we square it, it's going to give us a positive. So for what x values do we get it? Something that's greater than negative 1? Well, it's always going to be positive. So no matter what we put in, it's going to be greater than negative 1. It's actually going to be greater than 0 even. Well, it's going to be at least be 0. So it's kind of asking, when is You know, when are we going to have some number squared be greater than -1? Well, always. Okay, because we just said it's always going to be a positive solution, or positive result when we square something. So our solution set wants us to say what x values. Well, how do we say always, any x value? We can write that as all real numbers, is how we say that in words. But how we say that in interval notation is -infinity to +infinity. Okay, so that's one of the special cases. Let's look at the other special case. Again, we have something being squared, and we're saying where is that less than -5? Well, less than -5 is going to be less than some negative number. So this is asking, when could we have some number squared be less than a negative result? It will always be greater than a negative. When will it be less than a negative? Well, never. Again, we said it's always going to be positive. So it will never be less than some negative. Anything less than a negative will still be negative. So that will never be the case. So that's a situation where we say there is no solution. Or they might have you write in a null set, which means no solution. Alright. So those are special cases of quadratics. If you catch those special cases, you won't have to do all the work that we just did on the last few examples. Okay. And the last part of the section looks at rational inequalities. Okay. We have fractions we're dealing with, and we're going to say where's a fraction either less than 0 or greater than 0? Well, two things we have to remember. If we get a 0 in the numerator of a fraction, that means that the fraction actually equals 0. Okay, if we have 0 over some number, that equals 0. However, if you recall with a fraction, the denominator equaling 0 means the fraction is undefined. We're not allowed to have a 0 in the denominator. So, the two cut points, our two critical x values that we need to find are the x values that make the numerator equal 0 and the numbers that make the denominator equal 0. So, to find our cut points, let's first find what x value is going to make the fraction equal 0. Then we can look at what is going to make the fraction be undefined. Well, we just said that if the numerator equals 0, then that makes the fraction equal 0. So we want to say what x value is going to make 2x plus 3 equal 0. Undefined is going to be when the denominator equals 0. So we want to say what x value will make x minus 5 equal 0. Okay. This left equation, we'd have to subtract 3 from both sides. It's going to give us 2x equals -3. Here we'd add 5 to both sides. We're going to get x equals 5. So this one's already solved. This just has one more step. Divide on both sides by 2. X equals -3 halves. Okay. So that right there found us our two cut points. Okay. So we want to draw in our number line. Okay. From -infinity positive infinity. Our two cut points were -3 halves and +5. Okay. So once again, this cuts our situation into 3 intervals. Interval A, we'll call it, interval B, C. So at interval, at -3/2, that's what made the fraction equal 0. At +5, that's what made the fraction undefined. And one thing, before we even go any further, when you have a value that makes it undefined, we always use parentheses for this when we write our answer in interval notation. We always end up using parentheses at that point. Okay. So that will be more when we get to the final answer. All right, so now we want to test where our fraction 2x plus 3 over x minus 5 is less than or equal to 0. So we want to pick a value for A, region B, and region C. So region A is anything to the left of -3/2. Okay. Well, -3/2 equals -1.5. So if we go to -2, that would be to the left of -1.5. So let's plug in -2 into that fraction. For x, we have 2 times -2 plus 3 all over -2 minus 5. That will give us a -1 over a -7 when we simplify. And that actually reduces to +1/7. So to answer our inequality, we're looking for when is it less than or equal to 0? Well, that's positive, so that's greater than 0. So region A is not part of our solution. Okay. Let's check region B, or interval B. Okay. Well, we need a number in between -3/2 and 5. 0 is going to be in between those. So plugging in 0 into the fraction for x, 2 times 0 plus 3 over 0 minus 5. That's going to give us a +3 up top and a -5 down below, which is a -3/5. Well, that is less than 0. So that region checks. That's going to be part of our solution. Lastly, we have to check region C. So anything that's to the right of +5. So we can use +6 to check. So plugging 6 in for x into our fraction, we have 2 times 6 plus 3 over 6 minus 5, which is going to give us 15 over 1, which reduces to 15. Is that less than or equal to 0? No, it's positive, so it's greater than 0. So region C, interval C, is not part of our solution. Okay. So to answer our question, I guess we're asking, so 2x plus 3 over x minus 5 is less than or equal to 0 only in region B. Okay. So writing that in interval notation, region B, it's less than or equal to, so at -3/2 is where equals 0, we get a bracket. But then remember, we only have a parenthesis and spots that are undefined. So this is the interval we need to describe. So to do that, bracket at -3/2, comma, +5, but we use a parenthesis. Okay. Parentheses,